Okay, so we have our first example, and in this example we're going to show the linearity uh, due to the biasing of the output stage. And as example we have the following amplifier. So two-stage amplifier, and we have a differential pair with active loads at the input, and then a common source at the output. So we have not discussed multiple stage amplifier until now, but we're just going to assume that we have this amplifier ready, and then we're going to test it. So the output stage, as I mentioned just now, it is a common source amplifier, and we have this current mirror bringing current to both sides, to the differential pair and to the output stage. And then I have connected this amplifier as a voltage buffer, and this amplifier, it is driving a load that it is quite low. It is 5 kilo ohms. So let's see, design defaults. So it is 5 kilo ohms, and then we can assume that this is just an external load to the chip. I have a decoupling capacitor to ground, that it is just stopping the DC voltage and currents. So for AC, this is going to work as a short circuit for AC signals. Yeah, okay, so I have this circuit, and then if I draw this circuit here again, what we have this circuit doing is the following. We have plus, minus, like this, and this is 5 kilo ohms. So I am assuming that this capacitor is just a short circuit for high frequencies. And then this is my V out. And then if I connect an input voltage of 300 millivolts, I expect 300 millivolts also going in the other side. So yeah, we have something like this here at the input with 300 millivolts. I will expect exactly the same coming out. This will be out, and this is be in. Okay. Now I have to be very careful how the bias of the output stage is given, because it has to be designed so that it can drive the output, the load that I have placed here, the 5 kilo ohms. Then if we see this output looks like this of this amplifier. The output of the amplifier look like this. Okay, so as I mentioned before, this capacitor, it is just to stop the DC currents, and just it will get charged with the voltage at the output, DC voltage at the output, so there is no DC currents flowing through this resistor. Now what it is important here is the following. If we see our circuit, we have this PMOS transistor here, M5, and then from the current mirror we have M6. So I have to be able to bias these two transistors so that the signal swing that they see is the signal swing that I expect at the output. In this particular case, I am assuming that I'm going to put 300 millivolts here. It's going to be 300 millivolts amplitude here, 100 millivolts. So I have to make sure that there is enough biasing for these two transistors so that they can handle a signal excursion of 300 millivolts over this load. Now for AC currents, this capacitor became a short circuit, so we're just going to erase it for a second here, and then let's change it to an AC analog ground. That I'm going to put it like this for the moment, and then the amount of current, the amount of AC current that this resistor will see, it is at least in this direction will be equal to, at least it will be 300 millivolts divided by 5 kilo. Okay, because this is the maximum signal amplitude, and this is equal to 60 microamp. This is the minimum current, and then the same if it is going in the other direction, then it will produce a plus minus voltage here. The negative voltage, it is going to be the same, minus 60 microamp are going to pass in this direction, meaning that this current source here needs to be at least 60 microamp so that it can produce this negative voltage here. If it is smaller than 60 microamp, it will not be able to produce this negative minus 300 millivolts, and then let's say that if it is just half, it will just clip the signal here and just delete this one. Okay, it will just clip there. So then I have to be very careful with the amount of current that I put at the output stage, that I bias the output stage. So this is one of the issues. The other issue is that I have to make sure that the VDS of the output transistors, in this case are these voltages here, are larger than the voltage swing. That it is because, as we remember from the lecture on devices, the transistors need to work in the saturation region, and if they are in weak inversion, that means that VDS has to be somewhat larger than 4 times the thermal voltage, so this is around 100 millivolts. In practice, I need to take larger margins because over corners and process variations and temperature, this will be different. So, but at least I need to take 100 millivolts plus the voltage swing. So if the voltage swing here it is 300 millivolts, I add at least 100 millivolts, then this VDS has to be larger than 400 millivolts, and then we will call it this one. Which number of transistor was it? It was 5. This VDS 5 has to be larger than 400 millivolts, and the one under it is 6. This one has to be 6 has to be larger also than 400 millis. So these are the two important conditions that this design has to fulfill. Now in this particular case, the signal it is swinging around DC voltage of 900 millivolts. The power supply it is 1.8 volt, and this is connected to ground 0 volts. And then when I have the capacitor here, this capacitor it is going to be charged to the 900 millivolts. Remember that the voltage swing here is 0 volts, so we will have 900 millivolts DC at the output. And that means that if this is 1.8 volts, my VDS is going to be equal to 500 millivolts in both sides, and in this particular case it is more than enough. If we have 900 millivolts for VDS5 and 900 millivolts here for transistor 6 M6, then I am quite above the minimum 400 millivolts that I need. And then the only thing that I have to make sure is that I have enough current to drive the negative part. The positive part, depending on the feedback, it can provide more current or less current depending on what is needed, but the current source is constant, so this will be my limiting factor, the current source. Okay, so let's have a test to see what happens if I don't have enough current. So we go to our cadence, and then in this particular case, let's see, we have 10 microamps multiplier 4, it means that I have 10 microamps also here in the differential pair, and then I have a multiplier of 8, that means that I will have 20 microamps here. So let's run a very quick simulation, and then we annotate the DC voltages, and then annotate also the operating points. So I annotate the operating points, and then we see we have 20 microamps as we expected. Then let's take a look the transient results. As I mentioned, I put 300 millivolts input signal at 1 kilohertz. So let's take a look what happened at the output. And then what we have, it is as we expected. It is not enough. We needed at least 60 microamps, and the fact that we have only 20 microamps in this current source results in that the lower part of the signal, it is clipped. Yeah, so it just managed to amplify it at around this level, and then it is just clipped. And this is very important because sometimes we might think that the strong nonlinearities, the clipping, distortion happens only close to VDD and ground, but that is actually not true. If we have designed it wrong, we have dimensioned it wrongly the biasing of the last stage, the signal will just clip at any voltage. So this is good example. So let's try to make it a little bit better. We will let's leave it here. Actually, we are going to append it to the same graph to see the change. So we are going to provide a little bit more current. We're going to double this current, or we're going to, let's say, now we are in 20, let's make it 40. That means that I need to put 16 here to double the size of the transistor. Save, we run it. Then we have 40 microamps passing here, 40 microamps passing here, and then let's take a look to the transient simulation, and then we see from the original, then it's much better, but still it is not solved the problem because now we have only 40, but we need at least 60. So we're still clipping the signal, the lower part of the signal. So let's try to go back. So according to all calculations, we require 60. So that will be 24. We put 24, and then that will give us 60 microamps, that it is the absolute minimum that we need to be able to drive that resistance. And then we get the 60 micro, and then we take a look to the output. And then now we have the full signal swing at the output. Okay, we have the full signal swing at the output. Then now the buffering, it is linear. Yeah. Now, in theory, we need 60 microamp, but in practice, we need to take a lot of margins because components will behave differently over corner and Monte Carlo process and voltage variations. So we need to take margins, and then that will really change from application to application. Not only the transistor will change the performance, but there will be cases in which you're driving resistors on chip or capacitor on chip, and those have very large variations. So let's take around 30% margin. So we can put this one in 36. So instead of 60, we are going to be going to let's see, to 90. Okay, so with 90 microamps, and let's take a look. Okay, so we have basically the it's very linear signal. So okay, so important again, summarize it, this part. The dimensioning of the output stage is extremely important. Both the voltage swing and the current that it is fed to the load needs to be dimensioned correctly. I mean, it is the load and it is also the feedback. In this case, there is no feedback because the output is directly connected to the negative input, is a buffer. But if there is feedback, we will also have to dimension the feedback. An important detail, it is not only the resistances that have to be considered. We need to consider also capacitors. I mean, if we have capacitive loads, those capacitive loads will also require current at high frequency, so we have to calculate the impedance at the highest frequency of interest and then dimension the current that it is needed to drive that impedance in parallel to the resistors that we have, etc. So in this particular case, this capacitor is just a short circuit because it is connected in series, but if it had been in parallel, then we will have needed to calculate the impedance of that parallel capacitor in parallel to the resistor to find the right current that it is needed. Okay, so and then the VDS. I mean, the VDS in this particular case, we have almost 900 millivolts here at the output, so there is around 900 millivolts VDS for the output transistor M5 for M6, so there is enough voltage swing available for the output. Okay, so this is the first example.